At this very moment, while you are listening to these words, something rare and deeply unsettling is unfolding roughly 93 million miles away. On the surface of the Sun, the vast nuclear engine that sustains life on Earth, a massive scar has opened. Even more concerning, it has now rotated into a position where it is facing our planet directly. This is not a theory. It is not exaggerated storytelling. This is a real, ongoing event taking place today. December 4th. 2025, and what follows may permanently change how you understand the fragile relationship between Earth and the star that makes life possible. The Sunspot complex, known as AR 4294 through AR 4296, spans more than 350 kilometers. To put that into perspective, you could line up 27 Earths side by side and still fail to match its width. This makes it the largest sunspot formation observed in more than 10 years. Crucially, it has now rotated into a geo-effective position, meaning that any eruption, any sudden release of its stored energy, would be aimed directly at Earth. What truly alarmed scientists emerged when this structure was compared with historical solar records. The result was chilling. This sunspot complex is approximately 90% the size of the one responsible for the Carrington Event of 1859, the most powerful geomagnetic storm ever documented in human history, unlike the mid-19th century. However, modern civilization is now entirely dependent on technological systems that such a storm could severely damage or destroy. To understand why this situation matters, we first need to clarify what sunspots actually are. They are often imagined as simple dark patches on the sun's surface. But this description barely scratches the surface. A sunspot forms where extremely powerful magnetic field lines punch through the sun's photosphere, creating a region so magnetically intense that it suppresses the normal upward flow of hot plasma. This suppression causes sunspots to appear darker than their surroundings. Though they are anything but cool, their temperature still reaches about 500 degrees Celsius. They only appear dark because the surrounding solar surface burns at roughly 500 degrees. It is similar to observing a dim light bulb next to a floodlight. The bulb is still bright, but comparison makes it seem dark. What makes AR 4294 through 4296 especially dangerous is its magnetic classification. The U.S. National Oceanic and Atmospheric Administration has labeled this region as Beta Gamma Delta. These are not arbitrary terms. They represent increasing levels of magnetic complexity and instability. A beta classification indicates the presence of both positive and negative magnetic polarities. Gamma means those polarities are arranged chaotically rather than in a clean, organized structure. Delta, the most concerning designation, means opposite magnetic polarities are packed together within a single penumbral region. In practical terms, this is like forcing two immensely powerful magnets of opposite charge into direct contact, where their magnetic fields constantly twist, strain, and build tension like a tightly wound spring made of raw energy. This exact configuration is most strongly associated with the most extreme solar flares, X-class events, capable of reshaping Earth's near-space environment in a matter of minutes. Now here is where the situation becomes genuinely unsettling. On December 8th, 2025, just 3 days ago, the Sun unleashed an X1, 9-class solar flare. By any standard, this was a major event. It caused radio blackouts across Australia and Southeast Asia for roughly half an hour. Aviation communications were disrupted. Maritime signals failed. Earth's ionosphere, the electrically charged layer of the upper atmosphere, was suddenly flooded with intense X-ray and extreme ultraviolet radiation, altering its behavior almost instantly. However, there is a crucial detail that received little attention in mainstream coverage. That powerful X1, 9 flare did not originate from the massive sunspot complex we are discussing. Instead, it came from a smaller nearby region labeled AR 4,299. In other words, the disruption experienced just days ago was not caused by the main threat. It was merely a prelude. The giant structure rivaling the Carrington Sunspot has not yet released its primary energy, and there are growing indications that it may be preparing to do so. Solar observers have detected significant destabilization along the southern filament of AR 4294. A filament is a vast ribbon of relatively cool plasma suspended in the sun's corona by magnetic field lines. When such filaments become unstable and collapse, they can unleash enormous amounts of stored magnetic energy. More concerning still, filament eruptions can trigger what scientists call sympathetic eruptions, chain reactions in nearby regions. Much like a row of falling dominoes, one disturbance can set off another, leading to a cascade of events far larger than any single eruption alone. This is precisely what worries solar physicists right now. The December 1st flare sent a shockwave racing across the sun's surface. When that shockwave interacted with the already unstable filament near AR 4294, unmistakable warning signs appeared. The filament began to oscillate. Its anchor points brightened. Clear signatures of magnetic reconnection, the process that releases vast amounts of energy, were observed. If this filament fully destabilizes and its trailing structure connects with the main sunspot complex, the resulting eruption could be orders of magnitude more powerful than what occurred 3 days ago. To grasp the scale of what this could mean, we must return to the year 1859. At that time, English astronomer Richard Carrington was observing and sketching sunspots when he witnessed something unprecedented, a brilliant flash of white light erupting from the sunspot group he was studying, lasting roughly 5 minutes. 17 hours later, Earth would experience one of the most extreme space weather events ever recorded. Across Europe and North America, telegraph networks collapsed almost simultaneously. Communication lines that had once symbolized the cutting edge of technology failed in spectacular fashion. Operators reported being shocked by their own equipment. In some cases, telegraph paper ignited without any external flame. Even more astonishing, certain systems continued transmitting messages after being physically disconnected from their power supplies, driven solely by electrical currents induced by the geomagnetic storm itself. At the same time, the sky transformed. Auroras spilled far beyond their usual polar boundaries, illuminating the night as far south as Colombia and the Caribbean. In the Rocky Mountains, people awoke in the dead of night, convinced morning had arrived early. The heavens were glowing with an intensity few had ever witnessed. The sunspot responsible for this event occupied roughly 2/300 millionths of the sun's visible hemisphere. By comparison, the current sunspot complex measures approximately 2.080 millionths, about 90% of that historic size. However, it is critical to understand that sheer size does not dictate the destructive potential of a solar eruption. Magnetic complexity plays an equally decisive role. The orientation of magnetic field lines, the volume of energy stored within them, and how efficiently that energy is released all shape the final outcome. What can be stated with confidence is this AR 4294 through AR 4296 possesses the magnetic structure required to generate extreme solar flares. Whether it ultimately will remains uncertain, but the capacity is undeniably present. There is another aspect of recent events that has received surprisingly little attention. The coronal mass ejection associated with the December 1st flare was initially forecast to bypass Earth entirely. Early models suggested it would travel harmlessly into space, a near miss rather than a direct strike. Those projections turned out to be wrong. On December Dryad, the CME reached Earth, and the impact exceeded expectations by a wide margin. Instead of the anticipated G2-level moderate geomagnetic storm, conditions escalated to G3, classified as strong. The planetary K index, our primary indicator of geomagnetic disturbance, surged high enough to trigger auroral displays across northern Europe and large portions of the northern United States. This escalation did not occur in isolation. The storm's intensity was amplified by a rotating interaction region, Taurus or Sia Ardense, turbulent knot within the solar wind that reinforced the incoming CME. At the same time, a high-speed stream emanating from a coronal hole, an area of open magnetic field lines on the Sun, added yet more energy to the system. Together, these elements converged into a single, compounded disturbance. Each component strengthened the others, producing an effect far more powerful than any one factor could have generated alone. This convergence is deeply relevant to the situation unfolding now. If our predictive models underestimated the impact of a relatively modest CME originating from a secondary sunspot region, how reliable are those same models when applied to a vastly more complex and potentially dangerous source? The uncomfortable truth is that our confidence must remain limited. Solar physics has advanced enormously over recent decades. We can identify unstable magnetic configurations. We can estimate probabilities. We can issue alerts and warnings. But our ability to predict precisely when a sunspot will erupt and how powerful that eruption will be remains frustratingly incomplete. The Sun follows its own internal logic, one that does not bend to human timelines or technological preparedness. What is certain is that AR 4294 through AR 4296 will remain in a geo-effective position for the next 7 to 10 days as it moves across the solar disk. During this period, any major eruption would be directed squarely toward Earth. We are, in effect, staring down the barrel of a loaded weapon. That weapon may never fire. It could release its energy gradually through smaller flares and minor ejections, or it could unleash a single, concentrated eruption powerful enough to eclipse anything experienced in the modern technological era. Scientists around the world are watching with a mix of awe and unease. Events of this scale are rare, and they serve as living reminders that humanity remains deeply connected to forces far beyond its control, forces that have reshaped history before and may do so again. Yet the sunspot itself is only part of the story. The more pressing question is what a Carrington-class eruption would mean for a civilization built on satellites, global power grids, instant communication, and digital infrastructure woven into every aspect of daily life. To explore this, the European Space Agency recently conducted a detailed simulation of such a scenario. The results were sobering. Cascading system failures, prolonged outages, vulnerable choke points within global networks. Each layer of analysis revealed how exposed modern society truly is. The timeline of disruption alone demands careful attention. Adding to the unease are emerging patterns that suggest the Sun may be signaling something broader, cycles and rhythms that extend beyond the familiar 11-year solar maximum taught in classrooms. At the same time, subtle changes are being observed closer to home, deep within Earth's own interior. The timing of these phenomena may not be random, and there is one more critical detail that cannot be ignored. In the hours following the December 1st flare, solar observatories recorded something significant. The shock wave from the X-19 eruption did not simply dissipate into space. Instead, it rippled across the Sun's surface and interacted with a massive filament structure positioned beside the main sunspot complex. This filament, an immense arc of plasma suspended in the corona by opposing magnetic forces, began showing unmistakable signs of destabilization. What solar observers began to record in the hours that followed was deeply concerning. The filament exhibited a distinct oscillatory motion, accompanied by localized brightening at several anchor points, signals that physicists recognize as classic precursors to an imminent eruption. Its orientation is particularly troubling. Should this filament rupture, its magnetic structure would link directly into the unstable core of AR 4294, creating a pathway for energy transfer straight into the most volatile region of the complex. This is not a rare or hypothetical process. Nearly 30% of all major solar flares are believed to be triggered in exactly this way: external disturbances, destabilizing adjacent magnetic systems, and unleashing energy that has been quietly accumulating. In this case, the Sun appears to be methodically setting the stage. To understand why this moment matters, we need to examine what actually happens when a solar filament loses stability. The physics involved is both elegant and violent, and it reveals why even subtle changes can escalate into catastrophic events. Imagine a vast rope composed not of fibers, but of superheated plasma. Suspended hundreds of thousands of kilometers above the solar surface, there is no physical support holding it in place. Instead, it floats within the Sun's corona, balanced delicately by opposing magnetic forces. For days, weeks, and sometimes months, these filaments remain in a fragile equilibrium, gradually growing heavier as plasma condenses along their length. As they gain mass, the magnetic field lines supporting them stretch tighter and tighter, storing enormous amounts of energy. Eventually, that balance fails. The collapse typically unfolds in two distinct stages. The first is deceptively slow. The filament begins to rise through the corona at what, by solar standards, appears almost leisurely, on the order of 50 kilometers per second. This is the warning phase, though the warning is measured not in hours, but in minutes. As the structure ascends, it encounters resistance from the overlying magnetic field, an invisible cage that has confined it close to the Sun's surface. The interaction between the rising plasma and this magnetic barrier initiates a critical process known as magnetic reconnection. Opposing magnetic field lines snap, realign, and reconnect into new configurations. In doing so, they release vast amounts of energy, rapidly heating the surrounding plasma and accelerating the filament's upward motion. Then the second phase begins. The gradual ascent abruptly gives way to explosive acceleration. The filament is violently expelled, reaching speeds that can exceed 1,000 kilometers per second as it tears through the corona and erupts into interplanetary space. Magnetic reconnection intensifies, unleashing torrents of X-rays and extreme ultraviolet radiation levels sufficient to dramatically alter the ionosphere of any planet caught in the blast. When such a filament is magnetically linked to a sunspot, as appears to be the case near AR 4294, the consequences escalate further. The filament's eruption can act as a trigger, unlocking the vast reservoir of energy stored within the sunspot itself. Magnetic tension that has been building for days or weeks suddenly finds a release path. The result is a solar flare far more powerful than the filament eruption alone could ever produce. This sympathetic triggering mechanism is thought to be responsible for some of the most extreme solar events in recorded history. There is growing evidence that the Carrington Event itself may have involved precisely this type of cascading release, an initial disturbance, setting off a chain reaction across multiple active regions on the solar surface. When scientists examine AR 4294 through AR 4296 today, they see all the necessary components for such a cascade. Multiple sunspots packed closely together, each with highly complex magnetic topologies, filaments threading between them, acting as conduits for energy transfer. Unstable configurations capable of interacting, reinforcing, and amplifying one another's eruptions. It is, in every sense, a powder keg, and the December 1st flare may have ignited a very slow-burning fuse. The next question is unavoidable. What happens if that fuse reaches its end? Because when a major coronal mass ejection finally reaches Earth, the consequences are no longer abstract or theoretical, they become tangible, immediate, and potentially devastating. A coronal mass ejection is best understood as an enormous bubble of magnetized plasma, billions of tons of solar material hurled into space at velocities that can exceed 3 million kilometers per hour. When this expanding cloud collides with Earth's magnetosphere, the invisible magnetic shield that protects our planet, a dramatic transformation takes place. On the day side of Earth, the magnetosphere is compressed inward by the force of the impact. On the night side, it stretches far into space, forming an elongated magnetic tail that can extend millions of kilometers. If the magnetic field carried by the CME is oriented opposite to Earth's own, a configuration known as southward Bs, the two fields can merge through the same reconnection process that drives solar eruptions. When this happens, solar energy flows directly into Earth's magnetosphere. Radiation belts are supercharged. Powerful electrical currents surge through the upper atmosphere. These currents then induce secondary currents in any long conductive structure on the planet's surface. Power transmission lines, oil and gas pipelines, railway networks, undersea telecommunications cables. The longer the conductor, the greater the induced current. And this is where modern civilization reveals a vulnerability that would have been unimaginable to Richard Carrington in 1859. Modern power grids were never built with the sun in mind. They sprawl across continents, linking distant generating stations to dense population centers through transmission lines that stretch for thousands of kilometers. Under normal conditions, these lines are the arteries of civilization. Under extreme space weather, they become something else entirely. During a major geomagnetic storm, these long conductors behave like enormous antennas. They intercept the fluctuating magnetic fields driven into Earth's atmosphere and channel that energy straight into the grid. The resulting geomagnetically induced currents do not behave like ordinary electricity. They are slow, quasi-direct currents, fundamentally incompatible with the systems designed to manage alternating current at precise frequencies. When these currents enter a transformer, they force its iron core toward magnetic saturation. The device begins to heat unevenly and uncontrollably. Internal hotspots form where none were ever expected. Insulation breaks down. In moderate storms, this leads to inefficiency, shortened lifespan, and costly maintenance. In extreme storms, the outcome is far worse. Transformers do not simply shut off. They fail catastrophically. Internal components overheat to the point of melting, fusing copper windings and steel cores into solid masses that cannot be repaired. Once this happens, the transformer is permanently lost. And this is where the danger becomes systemic. Large power transformers are not interchangeable parts stored in warehouses. Each one is custom built, tailored to a specific location and load. Manufacturing a single unit can take 12 to 18 months under ideal conditions. A storm capable of destroying dozens or hundreds of transformers simultaneously would not cause a temporary blackout. It would initiate a prolonged energy crisis measured in months, possibly years. History offers a warning. In March of 1989, a geomagnetic storm triggered by a coronal mass ejection, far weaker than a Carrington-class event, brought the Hydro-Quebec power grid to its knees in just 90 seconds. 6 million people lost electricity for 9 hours. A transformer in New Jersey suffered irreversible damage. Voltage irregularities and equipment failures rippled across the northeastern United States and into parts of Europe. And that storm was only a fraction of what the Carrington event likely produced, perhaps 3 to 4 times weaker. Scale those impacts upward, and the implications become impossible to ignore. It is no coincidence that governments and utility operators have begun treating space weather as a critical risk over the past decade. Earlier this year, the European Space Agency ran a detailed simulation designed to test response protocols for a Carrington-class solar storm. The results were deeply unsettling. Within 8 minutes of the initial solar flare, intense radiation disrupted radar systems, GPS signals, and high-frequency communications across the sunlit side of the planet. Emergency services struggled to coordinate. Aircraft in flight lost reliable navigation. Ships at sea found themselves unable to determine their positions with confidence. Minutes later, a torrent of high-energy particles swept through Earth orbit. Satellites were bombarded with radiation that corrupted onboard memory, scrambled sensors, and in some cases inflicted permanent hardware damage. The simulation estimated that atmospheric heating would increase drag in low Earth orbit by as much as 400%, dramatically accelerating orbital decay. Hundreds of satellites would face destabilized trajectories, some re-entering the atmosphere uncontrollably. But the most severe consequences arrived roughly 20 hours later, when the coronal mass ejection itself struck Earth's magnetosphere. Geomagnetically induced currents surged through power grid infrastructure at levels exceeding 100 amperes. Protective systems tripped across multiple countries simultaneously. In areas where safeguards failed, transformers overheated, and some ignited. The interconnected nature of modern grids turned isolated failures into cascading collapse. As one region went dark, electrical loads shifted to neighboring systems, overwhelming backups that were never designed for such stress. Within hours, the simulation showed vast portions of Europe without power, without communications, without reliable transportation, without a clear timeline for recovery. This was not a speculative exercise. It was a physics-based scenario grounded in known vulnerabilities, using conservative assumptions. And it raises a question that grows more urgent by the day. If a storm of this magnitude were to strike now, would our systems bend or would they break? When the simulation concluded, the scientists involved offered an assessment that left little room for comfort. An extreme solar storm, they warned, carries the potential to damage or disable every satellite currently in orbit. The sheer volume of energy expelled by the Sun in a Carrington-class event would leave no spacecraft truly safe. Even satellites in low Earth orbit, normally afforded partial protection by the atmosphere and magnetosphere, would be exposed to radiation levels capable of overwhelming their shielding. The consequences of such a loss extend far beyond inconvenience. Satellites are no longer optional tools. They are embedded into the nervous system of modern civilization. Their sudden, widespread failure would cripple weather forecasting, disrupt financial systems dependent on precision timing, sever long-distance communications, and severely degrade military coordination across the globe. Entire sectors of society would be operating blind. There is a bitter irony in how familiar this risk is. For decades, researchers have outlined these vulnerabilities in painstaking detail. The solutions are not mysterious. Harden key sections of the grid. Install blocking devices on the most critical transformers. Stockpile spare components for rapid replacement. The estimated cost to protect the most vulnerable 1,000 transformers in the United States is roughly $100 million, an amount so small it barely registers within a federal budget. It is less than the price tag of a single major hurricane. And yet, those investments remain incomplete. Instead, we monitor the sun and hope. We issue forecasts and warnings, fully aware that even the most accurate prediction offers only hours or days of preparation. A coronal mass ejection cannot be deflected or stopped. Like an asteroid on a collision course, it can only be observed, tracked, and endured. The best we can do is brace for impact and hope that the impact is not the one. The Sunspot complex currently facing Earth represents exactly the type of structure capable of delivering such a blow. Whether it will or not remains unknowable. The Sun does not explain itself. It operates on timescales and energy budgets that render human concerns irrelevant. But at this point, the story begins to widen in an unexpected way. Because the Sun is not the only source of electromagnetic disruption demanding attention. Subtle changes have been detected closer to home, measured not in the solar corona, but in the ionosphere above us and the crust beneath our feet. Signals that appear before earthquakes. Anomalies that manifest hours or even days before the ground begins to move. Scientists have been tracking these precursors with increasing precision, and what they are uncovering challenges long-held assumptions about how Earth's systems interact, not just internally, but with the space environment beyond our atmosphere. Then, while much of North America slept, the first act of this unfolding sequence arrived. The coronal mass ejection launched by the December 1st solar flare reached Earth roughly 48 hours after leaving the Sun. traveling at speeds approaching 700 kilometers per second. Its encounter with Earth's magnetosphere occurred at approximately 1800 Universal Time on December 3rd. Almost immediately, instruments monitoring the geomagnetic environment began registering activity that exceeded prior expectations. The Space Weather Prediction Center had issued a G2, or moderate, storm watch for December 3rd and 4th. Given the data available at the time, this was a reasonable forecast. The CME appeared to be delivering a glancing blow rather than a direct strike. Most of the plasma, it seemed, would sweep past Earth instead of coupling efficiently with the planet's magnetic field. But space weather forecasting, for all its sophistication, remains an imperfect science. The models failed to fully account for what arrived alongside the CME. A rotating interaction region, a compressed boundary where fast solar wind plows into slower wind ahead of it, reached Earth at almost precisely the same moment. At the same time, a high-speed particle stream from a coronal hole injected additional energy into the system. The convergence of these three elements, the CME, the interaction region, and the coronal hole stream created conditions far more disturbed than any single component could have produced alone. Instead of the predicted G2 storm, Earth experienced G3-level geomagnetic activity. The planetary K-index surged. Aurora forecasts lit up across both hemispheres, from Oregon to Pennsylvania, from Washington State to New York. Observers reported seeing the northern lights rippling across skies that almost never host such displays. The aurora, beautiful as it is, represents visible proof of invisible violence. Those shimmering curtains of green and red are oxygen and nitrogen atoms high in the atmosphere, energized by electrons spiraling downward along magnetic field lines, releasing photons as they settle back into lower energy states. It is a reminder that Earth's magnetic shield is absorbing a sustained assault from particles carrying immense energy. The storm reached its peak around 3:30 p.m. Eastern Standard Time on December 3rd, maintaining G3 conditions for several hours before gradually subsiding. Ground-based stations reported degradation in high-frequency radio communications at polar latitudes. GPS accuracy dipped temporarily. Satellite operators observed increased atmospheric drag on low Earth orbit spacecraft as the thermosphere expanded in response to the incoming energy. These effects were noticeable but manageable. The grid held. Satellites survived. Infrastructure bent. But it did not break. And yet, this is precisely what troubles space weather forecasters. The storm that just passed was triggered by an X-19 flare from a secondary sunspot region, its impact magnified by timing and alignment with other solar wind structures. The main threat, the massive sunspot complex AR-4294 through AR-4296, has not yet produced a major flare from its current Earth-facing position. Instead, it has been steadily releasing M-class flares, 6 of them in the past 2 days alone. M-class flares occupy the middle tier of solar activity. They are strong enough to cause minor radio blackouts and localized disruptions, but rarely command headlines. What they do indicate, however, is sustained magnetic stress. Each M-class flare represents a partial release of energy, a small fracture along a much larger fault line. The unanswered question is whether these repeated releases are safely relieving pressure, or whether they are quietly loading the system for something far larger. And that uncertainty is where the real tension now resides. This uncertainty is not new. Solar physicists have wrestled with it for decades, and no one has found a fully satisfying answer. Some sunspot complexes vent their energy gradually, producing wave after wave of moderate flares before rotating harmlessly out of view. Others remain deceptively quiet, storing energy in silence, only to erupt suddenly with little or no warning. Despite our best models and constant surveillance, the sun does not announce its intentions in any clear or reliable way. All that can be said with confidence is that the ingredients for a major eruption are present. The magnetic topology is sufficiently tangled. The reservoir of stored energy is immense. Nearby filament structures show the kinds of instabilities that have triggered extreme events in the past. Whether that trigger will engage tomorrow, next week, or not at all remains genuinely unknown. For now, scientists watch and wait, tracking every subtle shift in the magnetic field, every oscillation along the filament, every brief brightening that might signal reconnection beginning. The sun holds all the cards. We are simply observers, trying to interpret patterns written in plasma and magnetic force, while attention remains fixed on the star above us. Something quietly unusual has been unfolding much closer to home within the ionosphere. The electrically charged layer of Earth's atmosphere stretching from roughly 60 to 1,000 kilometers above the surface. This region is exquisitely sensitive. It responds instantly to solar radiation, swelling and contracting with the day-night cycle. Solar flares drive sudden spikes in electron density. Geomagnetic storms ripple through it like shockwaves. But the ionosphere responds to more than just the sun. For decades, scientists have documented a puzzling phenomenon. Earthquakes leave detectable fingerprints in this upper atmospheric layer. This is not speculation, nor is it fringe science. Peer-reviewed studies going back many years show that the ionosphere behaves differently in the days and hours leading up to major seismic events. Measurements of total electron content, derived from GPS signal delays, reveal anomalous fluctuations before large earthquakes. The critical frequency of the F2 layer, the region most important for long-range radio propagation, shifts in patterns that correlate with impending ground rupture. These effects are not vanishingly small. They are measurable, repeatable, and increasingly predictable. A study published earlier this year examined ionospheric precursors associated with the magnitude 7.6 earthquake that struck near the Cayman Islands in February 2025. Researchers identified a structured sequence of signals. Acoustic gravity waves disturbed the ionosphere hours before more obvious anomalies appeared. Regional similarity indices shifted. Disturbance metrics rose. Rates of change indicated growing turbulence. The process unfolded in recognizable stages, each one providing additional warning that stress was intensifying deep within the lithosphere below. The framework that links these observations is known as lithosphere, atmosphere, ionosphere coupling, or LICE. The concept is deceptively simple. As tectonic stress accumulates in Earth's crust, it alters the physical and electrical properties of rocks. Piezoelectric effects in crystalline minerals generate electric fields. Microscopic fractures open. Radon gas, radioactive and highly ionizing, escapes from stressed rock and migrates upward through the soil. When this radon reaches the lower atmosphere, it ionizes nearby air molecules, creating localized electrical anomalies. These disturbances can propagate upward, modifying the electrical structure of the ionosphere far above the surface. Researchers have also identified another pathway, one involving heat. Prior to some major earthquakes, satellite-based infrared sensors detect localized thermal anomalies in regions that will later rupture. These temperature increases are modest, often just 1 or 2 degrees above background, but they are consistent and reproducible. A recent paper reanalyzing data from a 1969 earthquake on the Iberian Peninsula found clear thermal precursors appearing in the hours before the main shock. We have known about these signals for more than half a century. And yet, earthquake warning systems remain frustratingly limited. The connection to the current solar situation may not be obvious at first, but it becomes clearer when one key fact is considered: the ionosphere is the medium through which both solar disturbances and seismic precursors propagate. When a geomagnetic storm agitates this region, it can obscure, distort, or mask the subtle signals that might otherwise provide warning of an impending earthquake. At the same time, enhanced particle precipitation during solar storms may inject energy into Earth's atmosphere in ways that accelerate processes already underway in the crust. Earth is not a collection of isolated systems. It is a tightly coupled whole core, mantle, crust, atmosphere, and magnetosphere interacting continuously, exchanging energy across boundaries we once believed were separate. And that brings us to something even deeper, because beneath the crust, beneath the mantle, at the very center of the planet, another change has been detected, one that demands attention. Multiple independent research teams, using different seismic methodologies, have confirmed that Earth's inner core has altered the way it rotates relative to the mantle above it. The data is unambiguous. Something fundamental has shifted beneath our feet, deep within Earth. The solid iron inner core rotates inside a sea of molten metal, a hidden engine driving the planet's magnetic field. Over the past several years, scientists have detected subtle but undeniable changes in the behavior of that core, shifts in rotational speed relative to the mantle above it. On their own, these changes might seem academic, but when viewed alongside accelerating geomagnetic jerks, fluctuations in field strength, and subtle changes in pole drift, they begin to resemble pieces of a much larger pattern. The timing is difficult to ignore. The sun grows more active. Earth's magnetic shield shows signs of strain. Processes deep below the crust appear to be adjusting in ways we do not yet fully understand. None of this proves causation, but together, these signals form a tapestry that demands attention, and history offers a warning, one written not in speculation, but in direct human experience. On the morning of September 1st, Richard Carrington stood in his private observatory in Redhill, England. Engaged in a familiar routine, he was sketching sunspots, carefully recording their shapes and movements. Carrington was not a professional astronomer in the modern sense. He was an amateur in the original meaning of the word, a man driven by curiosity and devotion rather than institutional obligation. Having made his fortune in brewing, he retired early to devote himself entirely to the systematic study of the sun. His observations were meticulous, his records among the most detailed of his era. At approximately 1118 a.m. local time, Carrington witnessed something unprecedented. A sudden, brilliant flash of white light erupted from the sunspot group he was observing. Two intensely luminous patches flared into existence, moved rapidly across the solar surface, and faded within roughly 5 minutes. Carrington immediately understood that he had seen something extraordinary, even if he could not yet grasp its implications. In his published account, he noted that the event coincided with what was termed a magnetic crochet, a sudden disturbance recorded in Earth's magnetic field at observatories across Europe. Yet Carrington remained cautious. He famously wrote that one swallow does not make a summer, unwilling to claim a definitive causal link between the solar outburst and the magnetic disturbance. 17 hours later, caution was no longer possible. A geomagnetic storm of unprecedented intensity slammed into Earth, and the world was abruptly introduced to the power of space weather. Telegraph systems, the pinnacle of Victorian technology, failed across Europe and North America. In Boston, operators discovered they could transmit messages to Portland, Maine, with their batteries disconnected entirely. The system was being powered by electrical currents induced directly by the storm. Telegraph paper ignited. Operators suffered electrical shocks strong enough to knock some unconscious. The night sky itself became unrecognizable. Auroras surged far beyond their usual polar confines, illuminating skies as far south as Colombia and Cuba. In the Rocky Mountains, people awoke in the middle of the night, convinced the sun had risen early. The sky glowed with an intensity few living humans had ever seen. This was the Carrington Event. It remains the benchmark against which all geomagnetic storms are measured. Modern estimates place the flare responsible at roughly x45 in intensity, though such figures are necessarily imprecise given the instruments available in 1859. For comparison, the most powerful flare recorded during the satellite era was the X-28 event of November 2003. and even that may have been undercounted due to detector saturation. The Carrington event was almost certainly stronger, perhaps significantly so. Now comes the uncomfortable truth that governments, utilities, and insurers have begun to acknowledge only reluctantly over the past 2 decades. A Carrington-class event today would not merely be disruptive, it would be catastrophic in ways that dwarf anything in recorded history. In 1859, the storm damaged telegraph systems. In the modern world, it would touch nearly everything. Since Carrington's time, we have constructed continental-scale power grids, threaded with transmission lines stretching thousands of kilometers. We have built fiber optic networks that carry the bulk of global communication. We have launched satellite constellations that underpin navigation, weather forecasting, financial markets, military surveillance, and timing systems precise to the nanosecond. We operate pipelines controlled by electronic sensors, water treatment plants dependent on uninterrupted electricity, and hospitals whose life support systems cannot tolerate extended power loss. Our food distribution networks rely on refrigerated transport and just-in-time logistics that unravel within days if fuel and electricity fail. Every one of these systems contains vulnerabilities to geomagnetically induced currents, to electromagnetic disturbances, and to the cascading failures that follow grid collapse. Several years ago, the Lloyd's of London insurance market commissioned a detailed analysis of the risk posed to North America's power grid by extreme space weather. Their conclusion was stark. A Carrington-class storm could leave 20 to 40 million people without power, with outages lasting anywhere from 16 days to 1 or even 2 years, depending on how many large transformers were destroyed and how long replacements would take to manufacture. The estimated economic impact ran into the trillions of dollars. Globally, losses over a 5-year recovery period were projected to fall somewhere between $1 trillion. Numbers like these are so vast they become abstract, stripped of meaning. So let us ground them in lived reality. Imagine your city without electricity, not for a few hours, not for a weekend, but for 2 months or more. No refrigeration, no water pressure above a few floors, because electric pumps move water through modern buildings. No gasoline, because fuel pumps require power. No electronic banking, no ATMs, no credit card transactions. Grocery stores empty within days as supply chains collapse. Hospitals operate on dwindling generator fuel. Communication becomes fragmented, then scarce. Now extend that scenario across multiple states, or across entire countries, all at once. This is not a thought experiment. It is a plausible outcome, and it is within this context that the sun's current behavior takes on its full weight, not as an abstract scientific curiosity, but as a reminder that modern civilization rests on assumptions of stability that nature has never promised to honor. What follows in such a scenario is not immediate collapse, but something more insidious. Systems fail unevenly. Emergency services are quickly overwhelmed, not because responders stop trying, but because the tools they rely on no longer function. Dispatch centers lose connectivity. Medical facilities exhaust generator fuel faster than resupply can reach them. Life support equipment, dialysis machines, and refrigeration for medications become liabilities instead of safeguards. Communication degrades into fragments. Battery-powered radios, handwritten notes, physical messengers. Information moves slowly, imperfectly, and often inaccurately. In that vacuum, uncertainty spreads faster than facts. Civil order does not vanish overnight, but it strains. The routines that quietly hold society together begin to fray, and the implicit trust that institutions will always respond starts to erode. This is not speculation. It is the sober assessment of what a Carrington-class solar storm would mean for a civilization built on uninterrupted electricity and instant communication. And the sun has already proven that it is capable of delivering such an event. The Carrington Event itself occurred only 166 years ago, well within the historical record. Beyond that, the geological archive tells a deeper story. Ice cores and tree rings preserve evidence of even more extreme solar events in the distant past. One of the most striking examples is the Miyake event of 774 AD, revealed through a sudden global spike in carbon-14, recorded in trees worldwide. By current estimates, that event may have been an order of magnitude more powerful than Carrington. Similar signatures appear around 993 AD and at several other points over the last 10,000 years. These are not anomalies. They are part of the Sun's long-term behavior. The physics of stellar magnetism guarantees that such events will happen again. The only uncertainty is timing. It could happen tomorrow. It could happen generations from now. Statistical analysis suggests that Carrington-class storms recur roughly every 1 to 2 centuries, placing us squarely within a plausible window. Events on the scale of Miyake appear less frequent, perhaps once every 500 to 1,000 years, but that interval is long enough that technological civilization has never faced one, which brings the focus back, uncomfortably, to the present moment. The Sunspot complex, AR 4294 through AR 4296, is not destined to unleash a civilization-altering storm. Most sunspots do not. The odds against any single formation producing an extreme eruption remain significant. But this particular configuration is more concerning than most we see in a typical solar cycle. Its immense size, its tangled magnetic complexity, its direct alignment with Earth. Together, these factors elevate the risk above the background noise of solar activity. For the coming week, as this region traverses the face of the Sun, Earth occupies a period of heightened vulnerability. The appropriate response to this reality has been known for decades. Harden critical sections of the power grid. Install blocking devices to protect transformers from geomagnetically induced currents. Stockpile replacement components. Develop protocols for rapid, controlled grid disconnection if sufficient warning is available. Invest in space weather forecasting to maximize that warning window. These are not exotic technologies. They are practical engineering solutions to a well-defined engineering problem, and they could dramatically reduce the impact of even a severe solar storm. Yet progress has been slow. Utilities resist unfunded mandates. Regulators struggle to balance resilience against short-term costs. Political systems are poorly suited to prioritizing risks that may not materialize within a single election cycle. The result is incremental improvement real, but possibly insufficient. In effect, we are engaged in a slow-motion game of chance with the Sun, quietly hoping that the most severe outcome does not arrive before preparation catches up. Meanwhile, the Sun continues its cycles, indifferent to human schedules. Solar cycle 25 appears to be peaking now. In late 2024 and into 2025, sunspot counts are elevated. Flare frequencies are high. Overall activity suggests we are at or near solar maximum, the phase when extreme events are statistically most likely. The next few years represent a window of increased risk. This is not a call for panic. Panic obscures judgment and serves no purpose. But awareness matters. Understanding the fragility beneath our technological confidence matters. Preparation matters. The warning signs are visible to anyone willing to look. A massive sunspot facing Earth. A filament under strain. A geomagnetic storm that exceeded predictions only hours ago. These are not random occurrences. They are expressions of deeper processes that will, inevitably, produce an event larger than anything we are prepared to absorb. The only open question is whether that event arrives before or after we choose to act. And perhaps this is the most unsettling possibility of all. The warning signs do not end with the Sun. Some researchers argue that what unfolds in the solar system, what agitates Earth's magnetosphere, and what stirs deep within the planet's interior are not isolated phenomena. They may be linked through mechanisms we have only begun to glimpse, which brings the story downward far below the surface into the slowly churning iron heart of the Earth. where changes have been detected that defy easy explanation. The Earth does not always fail without warning. Before major earthquakes, subtle disturbances ripple through the ionosphere like whispers ahead of a scream. Total electron content shifts in patterns that solar activity alone cannot explain. The critical frequency of the F2 layer fluctuates. Acoustic gravity waves propagate upward from regions that will soon rupture catastrophically. The planet, it seems, communicates its distress quietly, indirectly, through channels we are only beginning to understand. And if those signals are real, if they are connected to the broader space weather environment surrounding our world, then the story we are witnessing may be larger than any single sunspot and far from over. For a long time, the idea that earthquakes could announce themselves in advance was treated as a scientific embarrassment. The history of earthquake precursor research is littered with overconfident claims, failed predictions, and public false alarms that eroded trust. Entire careers were damaged by association with the topic. Within the seismological community, skepticism hardened into something closer to taboo. Serious researchers learned quickly that attaching their names to prediction efforts could be professionally dangerous. And yet, the data refused to cooperate with that narrative. As satellite coverage expanded and measurement techniques improved, patterns began to emerge that could no longer be dismissed as coincidence. Independent spacecraft, operated by different agencies, recorded ionospheric disturbances repeatedly, coinciding with major seismic events. One of the most important contributions came from the French Demeter mission, a satellite launched with the explicit goal of studying earthquake-ionosphere interactions. Over years of observation, it documented consistent correlations between crustal stress accumulation and disturbances in the upper atmosphere. The more rigorously the data was filtered, the clearer the signal became. Something real was happening, even if the precise mechanisms were still being debated. Out of this growing body of evidence, the lithosphere, atmosphere, ionosphere coupling model emerged as the most coherent framework. According to this model, tectonic stress does not remain confined to fault lines deep underground. As pressure builds, it initiates a cascade of physical and chemical effects that propagate upward through the atmosphere and into near-Earth space. The process begins within the crust itself. Rocks subjected to extreme mechanical stress undergo changes in their electrical properties. Crystalline minerals exhibit piezoelectric behavior, generating electric fields in response to deformation. At the same time, microscopic fractures open within the rock matrix, creating pathways for gases trapped for millennia to escape. Among these gases, radon plays a critical role. Radon is a radioactive noble gas produced by the decay of uranium and thorium, naturally present in Earth's crust. Under normal conditions, it remains trapped in soil and bedrock, posing risks primarily in enclosed spaces. But when tectonic stress fractures rock, radon migrates upward through newly formed channels. Once it reaches the lower atmosphere, its radioactive decay ionizes surrounding air molecules, altering local electrical conditions near the surface. Those anomalies do not remain confined to ground level. Earth is enveloped by a global electric circuit, a continuous flow of current between the surface and the ionosphere. Changes in surface conductivity and electric fields modify this current flow, and those modifications propagate upward. At the same time, chemical reactions associated with gas release can generate subtle thermal anomalies. These localized temperature changes alter atmospheric density, launching acoustic gravity waves that travel upward through the atmosphere, mechanically disturbing the ionosphere. The result is not a single signal, but a layered warning system, electrical, thermal, and mechanical, activated as tectonic stress approaches a breaking point. This sequence was documented in remarkable detail during the February 2025 magnitude 7.6 earthquake near the Cayman Islands. Researchers identified a clear progression of precursors. Acoustic gravity wave disturbances appeared first, several hours before the rupture. Next came shifts in regional similarity indices, mathematical measures comparing ionospheric conditions across neighboring areas. Localized dissimilarity indicated a focused disturbance rather than a global effect. Following that, the ionospheric disturbance index rose, reflecting deviations in total electron content beyond expected norms. Finally, rate of change indicators spiked, showing rapidly increasing turbulence as electron densities fluctuated faster than normal. The entire sequence unfolded over hours, suggesting a theoretical warning window if the signals could be recognized and interpreted in real time. Similar patterns have since been identified elsewhere. Prior to the 2024 Noto Peninsula earthquake in Japan, synchronized anomalies appeared across land, surface temperature data, total electron content measurements, and electron density profiles nearly a week in advance. The 2023 Jishan earthquake in China produced high-frequency ionospheric perturbations consistent with acoustic gravity wave propagation. Again and again, the same message emerges: the crust does not suffer in silence. But this is where the story becomes more complicated and more unsettling. The ionosphere does not exist in isolation. It is simultaneously shaped by forces from below and from above. While tectonic processes disturb it from the surface upward, solar activity agitates it from space downward. During geomagnetic storms, the ionosphere becomes turbulent, noisy, and unstable. That turbulence can obscure the subtle signals associated with earthquake precursors, making detection more difficult. At the same time, some researchers have proposed a more provocative possibility. Rather than merely masking seismic signals, geomagnetic disturbances may sometimes act as triggers. Induced electrical currents flowing through Earth's crust during strong space weather events could modify fluid pressures within fault zones or alter the electrical properties of stressed rock in ways that reduce friction and hasten rupture. Statistical studies have identified correlations, controversial but persistent, between periods of elevated solar activity and increased earthquake frequency in certain regions. The mechanisms remain unproven. The evidence is incomplete, but the idea can no longer be dismissed outright. What is becoming increasingly clear is that Earth does not operate as a collection of independent systems. The Sun influences the magnetosphere. The magnetosphere shapes the ionosphere. The ionosphere responds to processes in the lithosphere, and the lithosphere may, in turn, be influenced by solar-driven electrical and electromagnetic forces through pathways we are only beginning to map. Our scientific disciplines have long been compartmentalized for convenience. Nature has never respected those boundaries, and as new data accumulates from satellites, seismic networks, and geomagnetic observatories, it suggests that the events we are witnessing now may not be isolated incidents, but interconnected expressions of a much larger, tightly coupled system, a system that may be approaching a threshold, and thresholds, once crossed, do not announce themselves politely. What followed was not clarity, but debate. As more seismic data accumulated, the picture became increasingly complex. Some analyses suggested the inner core was rotating faster than the mantle by a fraction of a degree per year. Others indicated periods where the rotation slowed, paused, or even reversed direction. The discrepancies were not trivial. They hinted that the inner core was not behaving like a rigid, predictable object, but as a dynamic system responding to forces we did not yet fully understand. For years, the disagreement persisted. Different seismic paths told different stories. Earthquakes originating in separate regions illuminated different slices of the core, and those slices did not all behave the same way. The inner core appeared anisotropic, its iron crystals aligned in preferred directions, meaning seismic waves traveled faster along some paths than others. This complexity made interpretation difficult and fueled skepticism. Then, gradually, a new consensus began to form. In 2022 and 2023, multiple independent research teams, using improved seismic catalogues and longer time baselines, arrived at a striking conclusion. The inner core's rotation had not merely changed speed, it had shifted phase. After decades of superrotation relative to the mantle, the inner core appeared to have slowed dramatically and possibly begun rotating more slowly than the rest of the planet. In other words, something fundamental had changed. This was not a measurement artifact. The signal appeared across different datasets, different methodologies, and different research groups. The inner core, once thought to be locked into steady motion, was now behaving like a pendulum, accelerating, decelerating, and potentially oscillating over multi-decadal timescales. The implications are profound. The inner core does not exist in isolation. Its motion is coupled to the liquid outer core that surrounds it, a vast ocean of molten iron whose turbulent convection generates Earth's magnetic field through the geodynamo process. Changes in inner core rotation alter the flow patterns of this liquid metal. Those altered flows, in turn, affect the strength, structure, and stability of the magnetic field that shields our planet from cosmic radiation and solar storms. Geomagnetic jerks, sudden changes in the rate at which Earth's magnetic field drifts, have already been linked to shifts in core dynamics. Accelerations in pole movement, regional weakening of field strength, an expanding South Atlantic anomaly where radiation penetrates closer to Earth's surface. These are not abstract curiosities. They influence satellite lifetimes, navigation systems, and the resilience of our magnetic shield. What makes this moment especially unsettling is timing. The apparent change in inner core rotation coincides with a period of heightened geomagnetic variability. It overlaps with an era of increased satellite anomalies, growing concern about pole drift, and now, a phase of elevated solar activity. None of these factors alone proves a connection, but together, they suggest a system under strain, a system responding to internal and external forces simultaneously. Earth's magnetic field has flipped polarity many times in the past. Those reversals are recorded in volcanic rocks and ocean sediments like a barcode of deep time. We are not in the midst of a full reversal now, but excursions, temporary weakening and wandering of the field have occurred more frequently than once believed. And weakening matters. A weaker field provides less protection against solar and cosmic radiation, amplifying the impact of space weather events. Which brings us back to the present, above us. The sun is active, its magnetic fields twisting and snapping around us. The magnetosphere absorbs repeated shocks. Within the ionosphere, disturbances ripple, sometimes masking, sometimes amplifying signals from below. And beneath our feet, in the deepest regions of the planet, the inner core is no longer behaving as it once did. These are not independent stories. They are chapters of the same one, a story about a planet embedded in a dynamic solar system, exchanging energy across boundaries we once assumed were stable. A story about thresholds, magnetic, mechanical, and electromagnetic that, when crossed, can reshape the environment we depend on. None of this implies inevitability. Earth has endured these processes for billions of years. Life has survived magnetic reversals, solar storms, and tectonic upheaval. But human civilization, optimized for efficiency rather than resilience, occupies a much narrower margin of tolerance. We built our world assuming continuity. The sun would rise, the grid would hum, satellites would orbit, the ground beneath us would remain still, until it didn't. Now we are learning that continuity is not guaranteed. It is negotiated moment by moment between forces vast enough to ignore our expectations entirely. And the deeper we look, the clearer it becomes that the signals are already there, not as alarms, but as patterns written in plasma, in magnetic fields, in seismic waves, and in subtle changes beneath the surface of the Earth. The question is no longer whether the planet is speaking, it is whether we are ready to understand what it is saying. This apparent slowdown marked a turning point in how scientists think about Earth's deepest interior. For decades, differential rotation had been treated as a steady background process, slow, predictable, and largely detached from events at the surface. But the realization that the inner core's motion could decelerate so dramatically, perhaps even stall, forced a reconsideration of long-held assumptions. The evidence did not come from a single data set or a lone research group. It emerged independently from multiple analyses using different seismic wave paths, different earthquake catalogues, and different modeling approaches. Waves that once arrived fractions of a second earlier now arrived later. Paths that had shown consistent trends for decades no longer did. The pattern was unmistakable. The inner core was no longer behaving as it had in the late 20th century. Some researchers interpret this as the midpoint of an oscillatory cycle, a moment when the pendulum pauses before reversing direction. Others argue it may represent a more profound transition, a reorganization of forces acting at the boundary between the solid inner core and the liquid outer core. The truth may lie somewhere between these interpretations. What is clear is that this is not noise. It is a signal, and signals in Earth's deep interior rarely remain confined. The interface between the inner and outer core is one of the most energetic and complex boundaries in the planet. Heat flows outward, material circulates, magnetic fields are stretched, twisted, and regenerated. Even small changes in the geometry or motion of the inner core can alter convection patterns in the surrounding liquid metal. Those altered flows propagate upward, shaping the geodynamo that sustains Earth's magnetic field. Magnetic field behavior over the past decade has been anything but stable. The North Magnetic Pole has accelerated its drift towards Siberia. Regional field strength has weakened unevenly, most notably over the South Atlantic. Satellite operators have been forced to shut down instruments during passes through this anomaly to avoid radiation damage. Navigation systems require more frequent recalibration. These are surface manifestations of deep processes. The coincidence in timing is difficult to ignore. A slowing inner core, a more variable magnetic field, increased geomagnetic disturbances driven by heightened solar activity. Each phenomenon has its own explanation. Together, they suggest a system experiencing adjustment across multiple layers simultaneously. Whether the inner core's recent behavior is purely internal or influenced by external forcing remains an open question. Energy from geomagnetic storms does not stop at the ionosphere. Induced currents penetrate the crust and mantle, dissipating energy as heat and modifying stress conditions over long timescales. Even small inputs can matter. Nature is patient in ways human systems are not. There is also growing evidence that the inner core's surface is evolving in shape as well as motion. Seismic reflections indicate that some regions are subtly rising while others sink, reshaped by gravitational coupling with the mantle and by flow within the outer core. These changes occur over decades, not millions of years rapid by geological standards. The inner core is not frozen in time. It is active, responsive, and dynamic. This reframes how we think about Earth itself. The planet is not a passive stage upon which solar storms and tectonic forces act independently. It is an integrated system, exchanging energy internally and externally, adjusting continuously to forces from above and below. The Sun agitates the magnetosphere. The magnetosphere interacts with the ionosphere. The ionosphere couples to the solid Earth. And deep below, the core responds in ways that may feed back into the entire system. None of this implies imminent catastrophe. Earth has endured these interactions for billions of years, but modern civilization has not. We exist within narrow tolerances. Reliant on stability, we rarely question. What makes the present moment notable is not any single measurement, but their convergence: a highly active sun, a disturbed magnetosphere, subtle but persistent ionospheric anomalies, a dynamically evolving inner core. These are the background conditions against which future events will unfold. And future events are inevitable. The planet will release tectonic stress, The sun will unleash powerful eruptions. The magnetic field will continue to evolve. The question is not whether these processes will assert themselves, but how prepared we are when they do. The signals are faint, they arrive early. They do not announce conclusions, only possibilities. They require patience, humility, and a willingness to look beyond disciplinary boundaries. Because the Earth does not warn us with sirens, it whispers first. And in those whispers may lie the difference between surprise and understanding. Geomagnetic jerks are subtle, but they are not minor. To the instruments that monitor Earth's magnetic field, they appear as sharp inflection points, moments when a long, smooth trend suddenly bends. To scientists, they are signals that something deep within the planet has shifted. These events are not generated in the crust or the atmosphere. They originate thousands of kilometers below our feet, in the turbulent flow of molten iron within the outer core. What makes geomagnetic jerks especially intriguing is their timing. They do not occur randomly. When researchers mapped their occurrence over the past century, a pattern began to emerge. Major jerks were recorded around 1901. Itenjo by Arshawu, Itenjo by Losajo, Itenjo by Tishaba, Itenjo by Josayi, Itenjo by Josajo, and the mid-2000s. Each marked a rapid reorganization of core flow, a sudden change in how Earth's magnetic field was evolving. And after many of these jerks, something else followed. In several cases, changes in magnetic pole drift accelerated shortly afterward. In others, regional field strength weakened or reconfigured. The South Atlantic anomaly, for example, appears to have intensified following the geomagnetic jerk of the early 2000s. Satellite measurements show that this region has continued to expand, exposing spacecraft to higher radiation doses and forcing operators to adapt or shut down sensitive instruments. Some researchers now believe geomagnetic jerks represent moments when the balance of forces in the core shifts, when flow patterns reorganize, perhaps in response to changes at the inner core boundary. If the inner core slows, accelerates, or alters its shape, the surrounding liquid iron must adjust. That adjustment propagates outward, eventually imprinting itself on the magnetic field we measure at the surface. This interpretation is controversial, but it is gaining traction. If correct, it means geomagnetic jerks are not just curiosities. They are surface expressions of deep planetary processes. They may be the first detectable signs that the geodynamo is entering a new phase, one that could unfold over decades rather than millennia. The mid-2000s jerk is particularly interesting in this context. It coincides with evidence that the inner core began changing its rotational behavior around the same period. It aligns with the acceleration of the North Magnetic Pole's drift. It precedes the growing concern over magnetic field weakening in specific regions. Individually, each observation has a plausible explanation. Together, they suggest coordination rather than coincidence. This does not mean a magnetic reversal is imminent. Reversals unfold over thousands of years, but excursions, periods of instability, weakening, and partial reorganization can occur much more rapidly, and even modest weakening matters in a technological age. A reduced magnetic field allows more energetic particles from the sun and cosmic sources to penetrate deeper into the atmosphere. It increases radiation exposure for satellites, disrupts navigation systems, and amplifies the effects of geomagnetic storms. In other words, it changes the boundary conditions under which modern civilization operates. What makes this moment unique is not that Earth's core is dynamic, that has always been true. It is that we are observing multiple indicators of change across different layers of the planet at the same time. Inner core motion, magnetic field variability, ionospheric instability, elevated solar activity. Each one interacts with the others, sometimes reinforcing, sometimes masking effects that would otherwise be easier to interpret. We are not passive observers standing outside the system. We are embedded within it, building infrastructure, launching satellites, transmitting power across continents, while the planetary machine beneath us shifts in ways we are only beginning to detect. The Earth is not a solid platform. It is a living engine of heat, motion, and electromagnetic force. The Sun feeds energy into that engine from above. The core releases energy from below. Between them lies a thin, fragile layer where civilization has flourished. Geomagnetic jerks remind us that stability is not guaranteed. They are punctuation marks in the long sentence of planetary evolution moments when something deep changes course. And if we are paying attention, they may be telling us that the system is entering a new chapter, one whose consequences will not be felt all at once, but gradually through more intense space weather impacts, more stressed technological systems, and a growing need to understand how the forces shaping our world are converging rather than acting alone. Because the most dangerous transitions are not the ones that arrive suddenly. They are the ones already underway. This is where caution becomes essential. Correlation is not causation. And history is littered with examples of humans projecting meaning onto coincidence. No serious researcher claims that geomagnetic fluctuations cause financial crises or political upheaval in any direct or deterministic sense. Human societies are complex systems shaped by economics, culture, technology, and chance. To suggest otherwise would be irresponsible. And yet, complexity cuts both ways. Complex systems are often sensitive to small perturbations. They can absorb stress quietly for long periods and then reorganize abruptly when thresholds are crossed. In neuroscience, tiny changes in neurotransmitter balance can alter perception and behavior. In ecosystems, slight temperature shifts can collapse entire food webs. In electrical grids, a single overloaded transformer can cascade into continental blackout. Human civilization itself is a complex adaptive system, composed of billions of interacting agents whose behavior is influenced not only by rational calculation, but by physiology, emotion, sleep, stress, and perception. If geomagnetic conditions subtly affect biological systems, as the evidence suggests they might, then periods of unusual magnetic variability could act not as causes, but as amplifiers. They would not dictate outcomes, but they might nudge already stressed systems toward instability, lower thresholds for conflict, reduce resilience to shock. The idea is uncomfortable precisely because it challenges the notion that human affairs unfold independently of planetary conditions. What makes the mid-2000s especially intriguing is that it represents a convergence, a geomagnetic jerk, accelerated pole drift, evidence of inner core transition. At the same time, the digital transformation of society reached critical mass. Social media platforms scaled globally. Information ecosystems fractured. Feedback loops intensified. Small signals suddenly propagated at planetary speed. Once again, no direct line can be drawn. But systems theorists would recognize the pattern immediately. Multiple subsystems undergoing transition simultaneously, each influencing the others through feedback rather than linear causation. And that brings us back to the present moment. Today, we are once again observing convergence, elevated solar activity, a magnetosphere absorbing repeated shocks, ionospheric disturbances that blur seismic signals, an inner core whose motion appears to be changing phase, a magnetic field exhibiting unusual regional behavior. These are not alarms, they are conditions. Conditions under which other events, natural or human, may unfold differently than they would have under a more stable background. The Earth has passed through such periods before. Life endured. The planet adjusted. What is new is the presence of a technological civilization whose infrastructure assumes predictability, whose systems are tightly coupled, and whose tolerance for disruption is remarkably low. Navigation depends on magnetic models remaining accurate. Power grids depend on geomagnetic quiet. Satellites depend on radiation levels staying within design limits. Human behavior depends. In subtle ways we rarely acknowledge, on biological rhythms tuned to an environment that has been stable for centuries. We are not passive passengers on this planet. We are participants in its energy flows, altering atmospheric chemistry, generating electromagnetic noise, reshaping surface conductivity, and probing the deep Earth with seismic waves and nuclear tests. We interact with the system even as it evolves beneath us. The danger is not that the Earth is changing. Change is its default state. The danger is assuming that those changes are irrelevant to us. Geomagnetic jerks remind us that the planet can reorganize internally on timescales that matter to human societies. Inner core oscillations remind us that stability at the surface depends on motion thousands of kilometers below. Solar storms remind us that our star does not recognize our technological maturity as a reason for restraint. Taken together, these phenomena suggest a world that is not broken but dynamic, responsive, and occasionally indifferent to our expectations. If there is a lesson here, it is not one of fear, but of humility. We have learned to measure whispers in magnetic fields, ripples in the ionosphere, delays in seismic waves that hint at motion in a solid iron heart. We are becoming aware that warning does not always arrive as catastrophe. Sometimes it arrives as pattern, and patterns only matter if we choose to see them, because the Earth does not pause for understanding. It continues oscillating, convecting, drifting while we decide whether we are merely recording its behavior or finally learning how to live within it. Uncertainty, in this case, is not a weakness of the science. It is an honest reflection of how planetary systems behave. Earth's magnetic field has never followed a simple script. It weakens, recovers, drifts, and reorganizes in ways that only become clear in hindsight. Once centuries of data are available, what makes the present moment unsettling is that many of the indicators we associate with past transitions appear to be active at once. A declining dipole moment, accelerating pole motion in one hemisphere and deceleration in the other, expanding regions of anomalously weak field strength, pulses of rapid secular variation linked to deep core flow changes. None of these, individually, proves that a reversal or excursion is imminent, but taken together, they suggest a field that is not in a steady state. And a magnetic field that is not steady changes how Earth interacts with space. A weaker or more disordered field allows greater penetration of energetic particles from the Sun. During periods of intense solar activity, this translates directly into stronger geomagnetic storms at the surface. Storms that might once have produced modest auroras could instead induce damaging currents in power grids. Radiation levels that satellites were designed to tolerate may suddenly exceed safety margins. Communication systems that rely on predictable ionospheric behavior become less reliable. This is why the timing matters. Solar Cycle 25 has delivered higher than expected activity. Large sunspot complexes have rotated into Earth-facing positions. Coronal mass ejections have arrived with impacts stronger than predicted. All of this is happening against a backdrop of a magnetic field that appears less capable of buffering those blows than it was a century ago. The Earth-Sun relationship is not static. It is a negotiation between forces that evolve independently and then interact. Which brings us back to the atmosphere specifically, to the strange and increasingly erratic behavior of the polar vortex. In recent years, cold air that was once reliably confined to the Arctic has spilled southward with growing frequency and intensity. Record-breaking freezes have gripped regions unaccustomed to such extremes. Jet stream patterns have become more distorted, lingering in place rather than flowing smoothly. Meteorologists describe this as increased waviness, blocking patterns, sudden stratospheric warmings followed by violent cold outbreaks. These are atmospheric phenomena, driven primarily by temperature gradients between the equator and the poles. But those gradients do not exist in isolation. They are influenced by how energy enters and moves through the upper atmosphere regions that are directly affected by geomagnetic activity. When geomagnetic storms inject energy into the polar ionosphere, They heat the upper atmosphere and alter circulation patterns in the thermosphere and stratosphere. This can weaken the polar vortex, making it more prone to disruption. A destabilized vortex allows Arctic air to plunge southward, while warmer air surges northward, amplifying weather extremes at mid-latitudes. This does not mean geomagnetic activity causes cold snaps. Weather remains a chaotic system with many drivers. But it does mean that space weather can modulate atmospheric conditions in ways that matter, especially when the system is already near a tipping point. Once again, the theme emerges amplification rather than initiation. Small perturbations do not create events on their own. They shape how existing stresses are released. The same principle applies below the surface. If the magnetic field is weakening and reorganizing, induced currents during geomagnetic storms penetrate more deeply into the crust and upper mantle. These currents dissipate energy as heat and can modify stress conditions in fault zones already close to failure. No one claims this guarantees earthquakes. But as with biological and social systems, the possibility that thresholds are lowered rather than crossed from scratch cannot be dismissed. Earth does not flip switches. It accumulates strain. The inner core oscillates. The outer core convects. The magnetic field responds. The atmosphere adjusts. The ionosphere vibrates. The crust deforms. Each layer exchanges energy with the others, sometimes quietly, sometimes violently. We tend to think of disasters as discrete events, a storm, an earthquake, a blackout. In reality, they are often the visible endpoints of long processes unfolding out of sight, processes that overlap, processes that interact. What we are witnessing now may not be a single crisis, but a convergence of cycles, a solar cycle near maximum, a magnetic field in transition, an inner core adjusting its motion, an atmosphere exhibiting increasing instability, a civilization more interconnected and more fragile than at any point in history. None of this guarantees catastrophe, but it does redefine risk. The future will not arrive as a single moment of collapse. It will arrive as a series of tests. Some will pass unnoticed. Others will expose weaknesses we did not know we had. The question is not whether Earth will change. It always has. The question is whether we will continue to assume that those changes are background noise, or finally recognize that we are living inside a system whose deeper rhythms are beginning to surface. This intrusion of Arctic air is not a single, isolated weather event. It is the surface expression of a deeper atmospheric rearrangement. The polar vortex has not simply weakened, it has deformed. Instead of remaining a tight, circular system centered over the pole, it has stretched, elongated, and fractured into lobes. These lobes act like channels, allowing cold air to spill southward while displacing warmer air northward in return. Such behavior has become more common in recent decades, and that trend has sparked an ongoing debate within climate science. Some researchers argue that a warming Arctic reduces the temperature gradient between the pole and the equator, weakening the jet stream and making it more prone to large, slow-moving waves. Others point to stratospheric dynamics, sudden warming events high above the surface that disrupt the vortex from above. Both mechanisms may be at work simultaneously. What is rarely discussed outside specialist circles is the role of energy input from space. During geomagnetic storms, large amounts of energy are deposited into the polar upper atmosphere. This energy heats the thermosphere and ionosphere, causing them to expand and alter pressure gradients that propagate downward. These disturbances can influence the stratosphere, the region where the polar vortex resides. When the stratosphere is destabilized, the effects can cascade into the troposphere, where weather actually unfolds. Once again, this is not a claim of simple causation. A geomagnetic storm does not cause a cold snap, but it can act as a perturbation, an added stress to a system already near a tipping point. In a stable configuration, such perturbations are absorbed. In an unstable one, they can redirect the flow of events. The current outbreak follows a pattern that atmospheric scientists are becoming increasingly familiar with. The cold arrives suddenly. It lingers longer than expected. Forecast models struggle to capture its persistence. Meanwhile, other regions experience unusual warmth, reinforcing the sense that the system has become unbalanced. For the people living through it, these distinctions matter little. What matters is the lived reality: frozen infrastructure, strained power grids, disrupted supply chains, and communities unaccustomed to prolonged cold pushed into emergency response mode. The very systems already vulnerable to geomagnetic disturbances, electric grids, fuel distribution, transportation are simultaneously stressed by extreme weather. This is where the threads of the story begin to tighten. A weakened or fluctuating magnetic field increases vulnerability to solar storms. Solar storms inject energy into the upper atmosphere. That energy can influence circulation patterns. Altered circulation increases the likelihood of extreme weather events. Extreme weather strains infrastructure. Infrastructure strain reduces resilience to the next disturbance, whether it comes from space, the atmosphere, or the ground beneath our feet. None of this requires conspiracy. It requires only interconnected systems operating near their limits. What we are witnessing may be less a series of unrelated crises and more a period of systemic sensitivity, a time when background conditions amplify events that would otherwise be manageable, a time when extremes of heat, cold, radiation, stress, and uncertainty become more common. The Arctic blast gripping the United States is a reminder of this fragility. It arrives not as a distant abstraction but as frozen pipes, closed schools, blackouts, and emergency shelters. It forces attention back to the basics: heat, power, water, food. It strips away the illusion that modern life floats above natural forces rather than resting precariously within them. And it raises an uncomfortable question. If the sun remains active, if the magnetic field continues to weaken or reorganize, if the atmosphere becomes more volatile, and if the deep earth continues its slow adjustment, what happens when these forces align more tightly than they have so far? We do not yet know. The models are incomplete. The data is still being gathered. The signals are real, but their interactions remain only partially understood. What we can say is this: the planet is not in equilibrium. It is adjusting, and adjustment, in complex systems, is rarely gentle. The cold that shouldn't be here is not proof of anything on its own, but it is part of a pattern of increasing extremes, deeper coupling between systems, and diminishing margins for error. The sun watches, the core turns, the field drifts, the atmosphere buckles, and humanity, standing on the thin skin between them all, is beginning to feel the consequences of living on a world that is very much alive. The consequences of such a convergence are difficult to overstate, not because they are exotic, but because they are brutally ordinary. Cold does not need to be dramatic to be deadly. Darkness does not need spectacle to dismantle order. When power disappears in sub-zero conditions, the crisis unfolds quietly, house by house, hour by hour. Heating systems fall silent, pipes freeze and burst, water pressure collapses in high-rise buildings. Backup generators run until fuel is exhausted, then stop. Hospitals are forced into triage decisions no modern society expects to face outside of war zones. Emergency shelters fill beyond capacity. Roads become impassable, not from snow alone, but from the absence of functioning infrastructure to clear them. Communication falters just when coordination matters most, and unlike a hurricane or an earthquake, cold does not pass quickly. It lingers. It punishes endurance. This is where cascading failure becomes more than an abstract concept. Electrical grids are engineered with margins, but those margins assume normal operating conditions. They assume predictable demand curves, intact transformers, functioning control systems, and rapid repair capability. They do not assume simultaneous geomagnetic stress, peak winter load, frozen access roads, and exhausted personnel. In such a scenario, even small failures compound. A single transformer damaged by induced currents becomes irreplaceable when transportation is disrupted. A regional outage becomes interregional as load shifts overwhelm neighboring systems. Grid operators are forced to make impossible choices about which areas to shed in order to keep others alive. Every decision creates second and third order consequences. And all of this unfolds not because of a single catastrophic blow, but because multiple stresses arrive at once. This is the uncomfortable lesson threaded through everything we have explored. The danger does not lie in any one system behaving strangely. The danger lies in synchronization. The sun does not need to deliver its worst. The magnetic field does not need to collapse. The atmosphere does not need to break records everywhere. They only need to align closely enough. Modern civilization is optimized for efficiency, not resilience. We rely on just-in-time supply chains, centralized generation, long transmission lines, satellite-dependent coordination, and public trust that systems will function tomorrow as they did yesterday. That trust is rarely questioned until it is tested. What we are witnessing now is not that test, but a rehearsal, a G3 storm instead of a G5, an Arctic blast instead of a continental freeze, localized strain instead of systemic failure. Each event, manageable on its own, reveals how thin the margins have become when combined. This is why scientists, engineers, and risk analysts increasingly speak in terms of compound hazards, not because they expect everything to fail at once, but because history shows that systems tend to break at their intersections, where power meets weather, where technology meets biology, where planetary dynamics meet human assumptions. The sun will flare again. The magnetic field will continue to evolve. The atmosphere will continue to surprise us. None of this is abnormal in Earth's history. What is unprecedented is a global civilization whose survival depends on uninterrupted coordination across all of these domains simultaneously. We are not facing an apocalypse. We are facing exposure. Exposure of fragility. Exposure of coupling we did not account for. Exposure of how quickly comfort can turn into vulnerability when background conditions shift. The question is not whether the planet will calm down. It will. Eventually. The question is whether we will use moments like this. Moments when the signals are loud but the consequences are still survivable to adapt. Because the systems beneath us, above us, and around us are not hostile. They are indifferent, and indifference, in a tightly coupled world, is far more dangerous than malice. There is a strange comfort in recognizing our smallness not as a surrender, but as a grounding. When we step back far enough, fear gives way to perspective. The forces we have been discussing are not malevolent. They are not targeting us. They are simply expressions of a universe governed by physics rather than intention. The sun does what stars do. The Earth does what planets do. Life, including human life, exists in the space between those realities. And yet, within that space, meaning still matters. Understanding the world as dynamic rather than fixed does not diminish human effort. It clarifies it. We are not meant to dominate the system we inhabit. We are meant to navigate it, to adapt, to pay attention, to build lives and societies that can bend without breaking when conditions shift. This is why the story does not end with catastrophe or reassurance. It ends with responsibility. Responsibility to design infrastructure that assumes disruption rather than perfection. Responsibility to invest in resilience instead of merely efficiency. Responsibility to educate rather than dismiss. To prepare rather than deny. Responsibility, above all, to remember that technology does not exempt us from nature, it binds us more tightly to it. The sky above us tonight looks calm. The ground beneath our feet feels solid. The systems that power our homes hum quietly in the background. These sensations invite complacency, but beneath that calm, Energy is moving. Magnetic fields are drifting. Plasma is twisting. Ice is surging southward. Iron is shifting deep below the crust. None of it waits for consensus. None of it pauses for comfort. And that is not a reason for despair. It is a reason for maturity. Civilizations are tested not only by what they can create, but by how they respond when creation meets constraint. The coming decades will not be defined solely by innovation or growth, but by adaptation, by how well we learn to live with a planet and a star that remain, ultimately, beyond our control. Tonight's exploration has not been about predicting doom. It has been about recognizing signals written in sunspots and seismic waves, in drifting poles and fractured vortices, in quiet data points that only reveal their meaning when viewed together. Those signals do not tell us what will happen next. They tell us that change is normal, that stability is temporary, that resilience is chosen, and perhaps most importantly, they remind us that awareness itself is a form of preparedness. To see the world clearly, not as we wish it to be, but as it is the first step toward living wisely within it. The sun will continue to rise. The earth will continue to turn. The field will wander. The cold will pass. And humanity will continue, shaped not just by the forces that act upon us, but by how we choose to respond. That choice quiet, unglamorous, deeply human is the one force in this entire story that truly belongs to us. And even after the lights dim and the screen goes dark, the story does not end, because this is not a narrative with a final chapter. It is a living process, unfolding whether we observe it or not, long after this moment passes, long after today's sunspot has rotated away and today's cold has loosened its grip. The same forces will still be at work quietly, relentlessly, without regard for our schedules or certainties. There is something profoundly grounding in that realization. We spend much of our lives consumed by urgency, deadlines, conflicts, fears that feel overwhelming when viewed up close. But when placed against the scale of a star that has burned for billions of years, or a core that has churned since the planet was young, those anxieties shrink to a more manageable size, not because they do not matter, but because they are not the whole story. Awareness does not solve every problem, but it changes how we carry them. To understand that we live on a moving planet beneath an active star is to recover a sense of humility that modern life often erodes. It reminds us that certainty is rare, that control is partial, and that resilience is more valuable than prediction. It invites us to replace the illusion of permanence with a practice of readiness, not fearfully, but thoughtfully. If there is a quiet invitation woven through everything we have discussed, it is this: pay attention. Pay attention to the sky, not as a backdrop, but as a system in motion. Pay attention to the ground beneath you, not as something inert, but as something alive with slow power. Pay attention to the signals, scientific, environmental, human, that suggest stress before failure and change before collapse. And pay attention to one another, because no model, no satellite, no instrument replaces the fundamental truth that human survival has always depended on cooperation, on shared knowledge, on trust built face to face. When systems falter, it is not technology that saves us first. It is people. The ancient civilizations understood this instinctively. They watched the heavens because they knew their fate was tied to forces beyond their control. We are rediscovering that truth, not through myth, but through data, through magnetometers and spectrographs and seismic arrays that whisper the same message in a different language. The universe is not quiet. The earth is not stable, and life has never required either to endure. What it requires is adaptability, curiosity, the courage to look without flinching, and the wisdom to act without panic. So as you rest tonight, know this: nothing is wrong with the world simply because it is changing. Change is the rule, not the exception. What matters is whether we meet that change asleep or awake. Tomorrow will bring new measurements, new interpretations, new debates. Some signals will fade, others will sharpen, and somewhere, deep below your feet and far above your head, the processes we have spoken about will continue unaware of your attention, yet profoundly relevant to your life. You are not separate from them. You never were. Stay curious, stay grounded, stay human, and remember, understanding the world is not about mastering it. It is about learning how to belong within it. The sun will rise again, the earth will keep turning, and you, for this night, are allowed to rest. Sleep well, my friend.